Here, the body is moving along the horizontal circle. Therefore, this type of circular motion is called horizontal circular motion. There is another kind of circular motion in which the body moves along the vertical circle. This type of circular motion is called vertical circular motion. In today's video, we are going to derive equations for velocity at different positions in vertical circular motion. As well as we are going to derive equations for energy at different positions while body performing vertical circular motion. Now the body is performing vertical circular motion tied to a string. A string is tied. At the end of the string, we got a body, and the body made to revolve in vertical circle. We know that the direction of linear velocity is always tangential to the circular path. So, at the topmost position, the velocity, that is v1, linear velocity v1 at the point A, and at point C, the linear velocity, at the point B, linear velocity. At the point B, the linear velocity is tangential to the circular path. Let us call it as a v2. And linear velocity at the point C, let us call it as a v3. We need to find expression for v1. We need to find expression for v3. We need to find out expression for v2. At topmost position, this is the direction of linear velocity. At topmost position, this is the center, and it is a rope thread, and the weight of the body is directed in the downward direction, as well as the tension T is also directed in the downward direction. But there is a one force, centrifugal force, directed away from the center, and centripetal force is directed toward the center. So these are the important observations. What are the first one? The weight equals to mg in the downward direction. Second one, tension in the downward direction. Third one, centripetal force is directed toward the center. This centripetal force provided by partly by the weight of the body and also partly by the tension in the string, and let us call the tension as a T1. So total downward force is nothing but mg plus T1. This is a total downward force. And one more force in the downward direction, that is a centripetal force, and this centripetal force is given by m v1 square upon r. This is the centripetal force. Therefore, the total force, that is mg plus T1, is equivalent to centripetal force, that is m v1 square upon r. Call it equation number 1. Now the body from top position comes, suppose, to the bottom position, from top position to bottom position. This is the center, and it is a thread, and it is a position B, and linear velocity v2, and the weight of the body acting in the downward direction, and tension is toward the center, as well as the centripetal force is toward the center. Therefore, centripetal force given by m v2 square upon r. So for position B, tension T2 is acting vertically upward direction. Weight of the body, weight of the moving body, the body making whirling around the circle, revolving in the circular path. So weight of the body is vertically downward direction, and therefore the total force in the upward direction is equals to T2 minus mg. Now this T2 minus mg must be balanced by the centripetal force, and that centripetal force for position B is given by mv2 square upon r. Call it equation number 2. The same equation we can also write T2 equals to mv2 square upon r plus mg. Implies we get the equation for tension in the string when the body is at position B. Even this is the same equation, so I can call it as the equation number 2. Coming back to earlier case where we got the equation number 1, mg plus T1 equals to m1 square upon r, mv1 square upon r. Now when the body at position A, the string was slack, implies at position A there is no tension in the string. Therefore when the body is at position A, tension in the string equals to 0. This idea will help us to find out the velocity, linear velocity of the revolving object at position A. Now putting T1 equals to 0. So we get mg equals to mv1 square upon r. M and m get cancelled both sides, implies v1 square equals to rg and v1 equals to under root of rg. So at position A, we have the linear velocity of the object is v1, and we got the formula for v1, that is v1 equals to under root of rg. This is the minimum velocity of the object at position A. Now let us draw the x. These are the coordinates. It is the x-axis and y-axis, and the point A is having coordinates x1, y1, and point B having coordinates x2, y2. So x1 is 0, y1 is r, and here is the coordinates of B, x2 0 and y2 minus r. Now as the particle moves from point A to point B, so particle is moving from point A to point B, so there is a change in the potential energy. As the particle is moving from point A to point B, there is a decrease in potential energy. So magnitude of decrease in potential energy is equals to m into g and change in the height of the object, that is y2 minus y1. Here we have taken positive modulus of y2 minus y1, so that is mg, and modulus of minus r, so that is equals to mg minus 2r, so that is equals to twice mgr. Therefore decrease in potential energy as the particle is moving from A to B is equals to twice mgr. Now the next step, change in potential energy is equals to change in kinetic energy as per as the law of conservation of energy. So change in the potential energy from position A to B, change in the potential energy A to B equals to change in the kinetic energy A to B. Change in the potential energy A to B, nothing but twice mgr. Now kinetic energy at point B is more compared to kinetic energy at point A. Therefore change in the kinetic energy Kinetic energy at B is how much? Half mv2 square. And kinetic energy at the point A, half mv1 square. Change in the kinetic energy equals to half mv2 square minus half mv1 square. Now simplifying, twice mgr equals to taking half common, taking m common, v2 square minus v1 square, and both side this m and m get cancelled. We get 4gr equals to v2 square minus v1 square. But what is v1? v1 nothing but under root of rg. We already got it. So putting that value here, 4gr equals to v2 square minus under root of rg. rg square implies v2 square equals to 4gr. Square of that, the root will go away, minus rg will come to the left side, it becomes plus rg. Therefore, v2 square equals to 5rg. Taking square root both sides, we get v2 equals to under root of 5rg. Therefore, we got expression for v2. v2 is the velocity of the particle at position B, and v2 equals to under root of 5rg. Whenever the particle is performing circular motion, very important thing is total energy of the particle is not changing. Now we already got the value of v1, that is under root of rg. We got value of v2, that is under root of 5rg. Now we need to find out velocity of the particle at point C. To find out velocity of the particle at the point C, we use idea, that is total energy at point B equals to total energy at point C. By using this relationship, we can find out velocity v3. That is kinetic energy at B plus potential energy B equals to kinetic energy at the point C plus potential energy at the point C. So kinetic energy at the point B is nothing but half mv2 square, and potential energy at B equals to 0, because the maximum energy, the total energy at point B is totally kinetic energy and potential energy 0. So half mv2 square plus 0, and kinetic energy at the point C equals to half mv3 square, and plus potential energy at point C equals to mgr. So half v2 is nothing but under root of 5rg whole square equals to half mv3 square plus mgr. This is equals to half m multiplied by 5rg, and here taking m common, so we get half v3 square plus gr. Both sides cancelling m. This is equals to half into 5rg equals to v3 square plus 2gr divided by 2. Both sides 2 get cancelled. Therefore, v3 square equals to 5rg minus 2rg. So v3 square equals to 3rg, implies v3 equals to under root of 3rg. Therefore, we got the velocity of the particle at point C, that is v3 equals to under root of 3rg. Now we'll find out expression for total energy of the particle at highest position. A is the highest position, A is the topmost position, and at the point A, we want to find out total energy. So total energy of the object at position A is addition of kinetic energy plus potential energy at point A. Kinetic energy given by half mv1 square, and potential energy is equals to twice mgr. Now we already know that the value of v1 is nothing but under root of rg So under root of Rg square plus twice mgr. This is equals to half m Rg plus twice mgr. This is equals to mgr plus 4 mgr divided by 2 equals to 5 upon 2 mgr. Therefore, total energy of the particle performing vertical circular motion at point A is equals to 5 upon 2 mgr. Now we need to find out total energy of the particle at lowest position. Again, the total energy at point B. Point B is the lowest position of vertical circular motion. Again, it is the addition of potential energy at B plus kinetic energy at B. At lowest position, the potential energy is 0 and kinetic energy given by half m v2 square. So that is equals to half m and v2 nothing but under root of 5gr. Therefore, total energy at B equals to half m and 5gr. This is equals to 5 upon 2 mgr. The total energy at point A was 5 upon 2 mgr and total energy at point B is also 5 by 2 mgr. So the total energy, the value of total energy is not changing in vertical circular motion. Now we need to find total energy at point C. Again, total energy at point C is nothing but kinetic energy at C plus potential energy at C. Kinetic energy half m v3 square and potential energy at point C is equals to mgr. So this is equals to half m and v3 nothing but 3gr under root of square plus mgr. This is equals to 3 upon 2 mgr plus mgr. Therefore, total energy at point C again 5 upon 2 mgr. So total energy at C equals to 5 upon 2 mgr. From above discussion, it is clear that total energy of the particle performing vertical circular motion at any point on its circumference will remain the same, that is 5 upon 2 mgr. Thanks for watching the video. Please write down your comments. Please like, share and subscribe the channel. Meet you again with another topic. Till then, wish you good luck. All the best.